Today we'll have a presentation by Andres about search for light mediators at CONNIE. So, Andres. Seus slides estão na mesma página.
Aqui?
Isso.
Okay. So, hello everyone. This is me again in another meeting. My third presentation here on YouTube. So today I'm gonna speak about the coherent neutrino nucleus interaction experiment in the searching of the light mediators. And so basically today I will speak a little bit about the CONNIE experiment and so on. So first I'm gonna give a little context. I will speak about the interaction that are being that the CONNIE is researching, the investigating. Then I will talk about the extension that they're making to the standard model. Later on, I will speak about the event rate for CONNIE experiment, how they estimate how they studies the extension of the standard model. And finally, I will speak about the search for light mediators by CONNIE. So here where I'm gonna give a little context. So the standard model predicted. So on one iteration, which name is coherent elastic neutrino nucleus scattering, or CFNS, which is the interaction of a neutrino or antineutrino with a nucleus given by these processes. And here we have a merely illustrative Feynman diagram. So we are going. So this is something that was predicted by the standard model, but it's pretty difficult to detect. It was predicted at the 17th, and only was discovered pretty late. But the thing is, predicted by the standard model, and it's difficult because it occurs at low energies, mainly at the keV scale. And then these processes, these kind of processes, help us to enhance the cross-section for scattering processes. This is a charge neutral current processes, so it's mediated by the C boson and so on. This occurs when the transfer momentum is less than the radius of the nucleus. Well, wait a minute, I will receive somebody here. That's a question? No, I don't see. No.
Now you can continue.
Okay. And so these processes only occurs when the transfer momentum is less than the radius of the nucleus. And the neutrinos or the antineutrinos generally have these energies of the range of the 50 MeV. So that's what these processes was discovered in 2017 and help us to establish new constraints on beyond standard model physics. So this is why it's important, these processes, for all the new physics that is coming around. So the standard model makes this description where I have the differential cross-section for the standard model, and I have all the kinematics terms involving the nucleus, the energy, the recoil energy for the nucleus, and the antineutrino energy. So this is depending of something called weak nuclear charge, the mass, and the form factor. This is the weak charge. This is for the nuclear weak charge, which depends on the number of neutrons and numbers of protons, and we have the Weinberg angle here, and this is the nuclear form factor. So which is given by this and depends on and has all these parameters. Here we have the range. At the range A, where the Yukawa potential dominates. And we also have the nuclear density, and it depends on the average radius of a proton in the nucleus. Enough.
Yeah, for no one
No, no more. For the in a nucleus. So this is only tells the form of the nucleus. So the station consists on adding a new mediator, in this case a light mediator as the C prime, which is a vector mediator, and we are considering a purely vector mediator. So the cross section, including this new mediator C prime, is proportional to the standard, to the differential cross section predicted by the standard model, but we have a new charge with the C prime boson, which is proportional to a new coupling constant and the mass of the C prime, which has to be lighter than the other bosons that we have in the standard model. So by assuming this is a Purely vector interaction, we can write the differential cross section, including this C prime, this new mediator, as shown in equation 2. Later on, we can assume also a light scalar, which is which we consider the Yukawa potential, and we assume that we do some assumption in the chirality. I don't remember which assumption specifically, but by this we can write the new differential cross section involving standard model and a light scalar mediator as the sum of the differential cross section for the standard model and the differential cross section assuming a new scalar mediator, which is gonna be proportional to this new charge for the light scalar mediator, which is gonna be proportional to the new coupling constant. And assuming that the couplets to the quarks are all the same, we can write this. We can write this coupling constant as this form, like a product of the coupling constant for neutrinos and for the quarks, and also again depending of the mass of the light mediator, of the scalar mediator. This is so here I've been showing how we have a new differential cross section for the standard model, for the for the vector mediator, and for the scalar mediator. So by this, we can have the event rate for CONNIE. So here we have again, this differential cross section, when can be given by the previous equation that shown, the equation 1, which for this is differential cross section for the standard model, equation 2, which is for the C prime mediator, and equation 3, which is for the scalar mediator. So also we're going to have a dependence in the number of nuclei in the detector. Then we are going to have some kind of threshold, which is going to be given by the minimum antineutrino energy in order that the nucleus has a recoil. And we have the differential floats for reactor antineutrino, and finally we can have the event rate depending of the efficiency of the detector, the signal that are gonna be have in the detector, and the measured energy. So with this, we can establish the search for light mediators motivated from the fact that we're gonna have non-standard interactions. This is just illustrative. It's something very illustrative. So we have a neutrino interacts with a fermion, and here we have this blob. There's something happening there, but we don't know. All the interactions that are happening there are non-standard interactions. And then what happens here, we're gonna have a neutrino, which can be the same, like in this case, can be this one also, or another neutrino, but these neutrinos are coming for a non-standard interaction. So that's why CONNIE studied the coherent neutrino nucleus scattering can establish new limits for low neutrinos coming from non-standard interactions. So here we have the limits. So this is so we have this one made by CONNIE, and we have this one, this dashed line, which corresponds to the standard model prediction. And by doing some calculus and looking by the plot, we can see that the event rates considering non-standard interaction, we are going to have that is 41 times greater than the one that is predicted by the standard model, mainly at the low energy range. So this is what CONNIE are looking for. They are studying the coherent and coherent elastic scattering. And by this, we have some limits for different kind of mediators. So we have this C prime mediator, and this is being studied in a sub-GeV mass scale for this mediator. And something that I want to show here is that for these masses less than 10 MeV, we're gonna have a more constraining region. So for CONNIE experiment in comparison with coherent, which is this blue curve, are gonna be more restricted here, considering one model, the Chavarria model, and this red considering the Littard model. So we are gonna have a more restricted region, a low mass regime, which is less than 10 MeV. This is for the vector mediator, and then for the scalar mediator, we're gonna have pretty much the same. It's only that the difference is that they're gonna have a larger range of masses, which is less than 30 MeV, and we're gonna have also for CONNIE that are gonna be more restricted, and these low masses. And so this is, since it is more restricted, CONNIE has more constraints in the limits, where we can say that the CONNIE experiment has the potential on studying the light mediator, to study the light mediator at sub-GeV scale.
So I have one question. Could you go back one slide? Do you know why this curve is flat? The blue curve is flat below 30 MeV, or the one before? Yeah, that one. Why is flat below 30 MeV?
Below 30 MeV.
And I also should tell you that this red curve from CONNIE will also become flat below 1 MeV. And those flatness, this plateau, happens for the same reason.
No, I don't know.
Now go back some slides. You have the answer there.
Because it's gonna be there will be a moment that will be independent of the mass, right?
Right. Okay. Yeah, there.
There.
No, one more way. It's more explicit. Yeah.
Here.
So see?
Yes, for lower mass are gonna.
So as soon as the mass of the mediator, in that case, Z prime mass becomes small. Smaller than what? Then 2m capital M. What's capital M?
Capital M, the mass of the nucleus.
Okay. So depending on the target you use, that plateau happens at different masses.
Different masses, yes.
Awesome. So CONNIE uses one target, coherent uses a different target.
Yes.
Okay, cool. And they have different ER.
Yes.
Energy recoil.
Energy recoil.
The energy recoil there is related to the energy threshold,
Yes.
which you showed later. You know what's the energy threshold?
The
Go forward. One more.
energy.
Yeah, there. See the
Yeah.
rate? No,
Yes.
this one. The rate goes from energy threshold to infinity.
Yes.
What is this?
Is the minimum energy in order to happen these events?
Yeah. So it's the minimum energy that the signal should have for me to detect it.
Yes.
So if perhaps if I have a different technology, my energy threshold might be different.
Yes.
If for each detector, we'll have an energy threshold. Okay, which will be based on the technology and the details of the detector. Coherent has one and the other one. So
Yeah.
this same logic that applies to neutrinos also applies to dark matter,
Okay.
and also applies to particle physics, and etc.
Okay.
So all kind of detectors, they have an energy threshold. They are just by nature.
Yes.
Okay, which is the energy required for the signal to deposit a signal. Notice the difference. This is a detector-oriented value,
Yes.
not theory. In the perfect world, I can always observe a signal,
Yes.
right? But the detector is limited by some circumstances that we don't know. And said, okay, maybe there might be a signal below 1 MeV, but I won't see it. So my detector, it can even see it, but it's
Yes.
unable to distinguish signal from background. Since
Okay.
I'm not capable of distinguishing signal from background, I set a threshold from that point on, I can distinguish signal from background, and then I set this value as the energy threshold.
Yeah.
Okay? You might even see, say, so CONNIE can never see a signal below the energy threshold. This is not true. You can see, you just cannot distinguish signal from background.
Okay.
So it's up to the experimentalist to determine which value should be.
Yes.
And that value is related to statistics. Let's say I want to impose 90 limits with 95 confidence level.
Yes.
Right? So I need to know with 95% of confidence level that if an event happens above the threshold, I can distinguish signal from background.
Yes.
So where this energy threshold will happen is strongly related to the statistics. Okay?
Okay.
All right. And then do you know how you're gonna, in the end, constrain content scattering?
Content scattering? Oh. Well, content scattering usually happens a certain range of energy, but I don't remember exactly at what range of energy happens this content scattering. I don't remember actually.
Yeah, even I don't remember. Do you remember that? She gave a talk about this, but no, Carla.
Oh, okay.
Carla gave a talk about this, but I asked her, she answered, but I forgot. Honestly, I forgot.
Okay.
Okay, awesome.
There's something in the meat?
So someone asked the question.
Can I ask a question?
Yes. Yes, Ricardo. Ricardo?
Hi. Can you listen to me?
Yes.
Can you go back to page 6?
This?
What is this LDM? It's light dark matter, right? Light dark matter?
Where? Light dark
In
matter.
the
Yes, light dark matter.
but in this model you're considering dark matter in this model because you only talked about the mediators.
Yes, we're considering the dark matter. It's an assumption
Okay.
made.
It's because it's common in experimental collaborations called the mediator as dark matter, but it's not dark matter.
Okay.
Okay. So the mediator is dark matter.
Yeah, they should refer
You're not like
sector, but because dark matter is sexy, then they say dark matter.
okay.
So they say we are probing
Yeah,
dark
So
matter.
in
Probably dark
Sub-GeV
matter.
dark matter. No, you're not probing sub-GeV dark matter. You're probing sub-GeV.
yeah, we could be probing a portal to dark matter or something like that.
But is it light dark matter or is it
Dark matter.
light dark mediator?
Yeah, I know.
yeah, I was thinking that maybe was like that mediator
But anyway,
also.
it might be
Yeah, it
that
makes sense.
Maybe it is
in
a
the
dark matter that they
paper
are not
later they
comparing.
interpret
Like dark matter.
there are fermion pairs that annihilate to
Yes.
the Higgs boson, and they plot in the same plane
No,
the
they don't.
coupling versus them, but they don't do this.
Yeah,
Okay,
they
so
just say this.
yeah, so whatever. They're just
They
motivating.
use this
Yeah,
to say that the scalar mixes with it.
yeah. So it's just because it's sexy. Yeah.
And they are considering some kind of gauge symmetry for these
Oh,
bosons.
they don't go into
in-
detail.
They don't
or
they,
it's
they
just,
didn't talk about any
yeah.
symmetry.
So for the
okay, as the primary.
Probably. You know.
let's say minimal extension to the
They don't care about this.
In,
So for those who were not there at the spring meeting 2 weeks ago, spring meeting, it was 2 weeks ago.
dark.
Contra Primavera? It was two
Yeah,
weeks
2 weeks
ago.
ago. So the spring meeting there, in some ways, there was one guy who gave a talk about nuclear physics.
Hmm.
I don't know for those who were there. He was really upset with dark matter and other topics.
I was there, I remember.
Yeah. So he was really upset with dark matter, and he was upset with dark matter. He was upset with LHC. He was upset with what else? Axions. He was upset. I mean, everything else which is a hot topic.
Yes.
Black holes. None of this exists.
It's a funny guy to drink with.
Anyway, you should know. And then he was really upset, and it's true. And he
Yes.
said, "Yeah, I like the bad mouth." He even, I quote, that's what he said. I like the bad mouth. He said.
You're like, what? Sorry?
These people just want to go do something, things that are easy. They don't want to do hardcore stuff like I do, nuclear physics.
Hmm.
That's exactly what he said, right? So you
Yes.
should not worry about neutron stars. Who cares about neutron stars? You should work on these other stuff, right?
Okay.
Yeah, but some people for us, I didn't care about what he said.
Yes.
But the guys from nuclear physics, I think they were not, did not take that easy.
Yeah.
It doesn't make any sense because we need the nuclear physics to build the detectors.
Yes, I saw that Vito has something to say.
Say it.
Can you hear me?
Yes.
Why are they considering just CONNIE, not CONUS? Because CONNIE has a worse resolution than CONUS, and the CONNIE has never measured the coherent nucleus scattering. So wouldn't it make more sense to consider the CONUS for that measuring?
They are studying the limits that CONNIE has. So until
Okay, so it's something from the CONNIE collaboration.
yes.
Okay. Now I got it. Thank you.
There's something more? Okay. Yes.
Yeah. This should not be public. But I can log in. I can use this laptop. I need to
Okay,
log
okay.
into my
Just
account. My
so thank you all for seeing the stream, and until next time.